Hi, I'm Josh Manning. Welcome to Red Hat Partner Connect. This is the second part of the Operator webinar series after the introduction, where we go into just an overview of Kubernetes and operators and how operators fit into the Kubernetes ecosystem, and also just a basic introduction of what they are. Let's start from the top. What is Kubernetes? Well, Kubernetes is a platform for managing containers. It's designed to run at scale and designed to run and deploy and manage containers at scale, be it whether that's just one virtual machine or one bare metal machine up to hundreds or even thousands. So think Google-esque scale. I mean, obviously this, for those who may not know, this project started at Google. It kind of evolved from their internal Borg software suite for managing their containers at scale internally at Google, and was open sourced and donated to the Cloud Native Computing Foundation, who will then, oversee that project moving forward. The architecture is a simple master node architecture, and what that means is you have control hosts, which are dubbed masters, and you also have compute hosts, which are dubbed nodes. Kubernetes provides resources that abstract things like containers, networking, storage, sensitive information such as SSL certificates, key pairs, and whatnot, and many other things that are like much more high level deployments, custom resources, and so on, which we'll get into as we move further through the presentation here. All resources can be defined in either JSON or YAML syntax. Just a little more in-depth on Kubernetes resources, just kind of a brief overview of what resources are built into Kubernetes here. First off, you have a pod, which is the base unit of measure in Kubernetes. It's made up of one or more containers. Think of like a pod of whales, like a group, not necessarily a one-to-one mapping, but you'll see a recurring theme here in the Kubernetes realm and Docker realm, where you have just kind of the whale and just nautical references and themes throughout here. But anyways, a pod, just basically a container's one or more. A service is a common network ingress point used to serve TCP/IP traffic to the pods. So this basically acts as a fixed IP address for the pods. Pods on the back end are ephemeral. They come and go. They're assigned IP addresses out of a pool, so there's no static way to communicate with a pod directly. So there's a service abstraction which acts as kind of a networking load balancer of sorts that sits in front of the pods at a network level. Persistent volumes are a common way to abstract persistent storage in Kubernetes. Pods can claim available physical volumes by using a persistent volume claim, which is a YAML or JSON declared file, which goes in and you would specify what type of storage you want and like what the minimum size would be. So when you create a claim, Kubernetes will see your claim and try to match that according to what's available from its pool of persistent volumes. Aside from persistent volumes, pod storage is otherwise ephemeral in the nature of pods or containers themselves. Secrets, these are used to store sensitive information. Like on the previous slide, SSL key pairs and things of that nature could be auth secrets, auth tokens. These are base 64 encoded, so they're not truly secrets. They are reverse encodable. But there's just a way to map things like SSL keys that wouldn't necessarily be baked into a container image, but you do need a common way to access these types of things and be able to map those as a kind of a storage unit into the pods themselves. Configuration maps, these are used to manage common configuration files across pods. Think of one static configuration file that you could edit to be able to update the configuration across many pods on the back end. Kubernetes Resource Example. Here we have key components of Kubernetes resources in a YAML syntax. Just an example basic pod definition here, just to kind of show you what are the key aspects here. We have API version, the kind of resource being consumed or declared here, which is a pod. You'll notice the syntax here when you declare a kind in a Kubernetes resource is that they're usually init caps. You'll notice this also with Kubernetes custom resources, and we'll get into that more later. Metadata is where we declare the name of this instance of the pod. So my app-pod. And we can also apply any labels, any key value pairs there that we just want to associate with this particular resource or this pod. And the spec field there, containers, and this is where we basically define all resource-specific attributes such as state. You'll see the name of the container itself, the image being consumed, the Docker image, BusyBox, and even a command which launches a shell and does kind of a hello world type message and then falls into a sleep state. The API version, going back to that, you'll notice it's just v1 because Kubernetes upstream is still at version 1.x. 2.x is on the horizon, so this likely will change with Kubernetes 2.0 and OpenShift 4.0 moving forward. Some of the higher level resources in Kubernetes. So first off, you have deployments. This is essentially kind of a higher level pod declaration, but it provides declarative updates. And it means to trigger rolling updates. So if a change to a deployment is detected, say you've changed the number of pods you want running, if you change the deployment, it will start a fresh rolling update and launch a new set of pods and gradually terminate off the old pods. This is often used in conjunction with operators. This is how operators get deployed. This is the resource that would deploy the operator image itself into Kubernetes. Daemon sets are similar to deployments, but they're used to basically ensure a one-to-one mapping of a pod to an actual node or a compute host. So if you have things like configuration management agents, Puppet logging agents such as FluentD, or monitoring agents, so this is useful for that. Stateful sets, similar to deployments still, kind of building on that, but these are for resources such as storage or networking IDs to make those stick to pods. Pods are ephemeral in nature, but certain things like databases tend to work better if they have network storage volumes that stay with their actual individual pods and don't go away. Same thing with maybe the pod's IP address, not the service IP, which is that fixed static IP address, but also get the actual pod network address to stay with the pod. Replication controllers, these are used to ensure a certain number of pods stay running at all times. It's essentially a lower level form of deployment. A deployment is specifically just a higher level form of replication controller. Like I said, we declare that we want a certain number of pods to stay running, and if one pod goes down, Kubernetes will try its best to maintain that state and will kick off another instance of the pod so that there's always a minimum number of what you specify in a running healthy state. Replica sets, these are kind of like the next generation replication controllers. They're functionally equivalent to a replication controller at this time, but they support a new set-based selector label, which gives some interesting ways to select nodes by their tags and like pattern matching and substitution and things of that nature, which is more advanced than a simple one-to-one just match a key value pair. So then what are operators? Operators are methods of packaging, deploying, and managing a Kubernetes app. And a Kubernetes app we define it as an application that's both deployed on Kubernetes and managed by Kubernetes APIs and the client tooling. Client tooling for upstream Kubernetes is the kube control command, and the equivalent of that for OpenShift is the OC command or OpenShift client, otherwise known as OC. An operator encodes human operational knowledge into software, whether this is a system administration task, database admin and maintenance task, backups, migration and restoration, application lifecycle management. These are things such as stage rollouts or blue-green deployments. And you can also have automated deployment of, say, an entire Kubernetes cluster in the case of Tectonic, and this functionality soon making its way into OpenShift, where we will have automated rollout of an entire OpenShift cluster, hands-off, no need for Ansible playbooks, and also atomic over-the-air updates as well. This is all accomplished by basically extending the Kubernetes APIs and adding in their application-specific logic. There are two primary components of an operator. The operator image itself, which contains the Go code and all the logic therein, the brains of the operator, and the custom resource definitions, which registers with the cluster the type of custom resource that the operator is consuming. This is basically the resource or the application level resource that the operator is managing for us. Custom resource example, here as in the pod definition we've shown earlier, you'll notice the same structure. So all these elements are pretty much in every Kubernetes resource. You have the API version here in the format of just a vendor organization website /version. Here we have app.example.com/vendor v1 alpha 1. And the v1 alpha 1, that's an arbitrary version. It's a little scary to see. You'll see alpha branding in a lot of the operator frameworks and things. That's going to go away as this stuff becomes more stable and proven, and adoption gets taken up. We're in the early adoption stages now, so we're just trying to get kind of a community built around operators and just kind of a foot on the ground there. But anyways, the v1 alpha 1 in the API version, like I said, is arbitrary. It could be v1 beta 1, v2, v3, v4, but that's pretty much explains that. Moving on to kind, here we just have example app. So for a Kubernetes built-in resource, this would be pod or service, but in this case we have an actual application being managed by a Kubernetes API or Kubernetes controller. In this case, that kind is example app. The metadata, once again, this is the name or the instance name for this particular custom resource, my-example dash app that's being deployed. And the spec here, so for a simple operator, you might just want to get something started for just a size. So I just want a scale to be able to scale the deployment and set a size in the custom resource. And the custom resource is essentially how the user interacts with the operator, and we'll get more into that later. But what are the common development methods? Here are basically three of the most common ways. The Helm app operator kit is a means to develop an operator using Helm chart. So the operator image basically gets built with a Helm chart baked in. It's the quickest and easiest way to develop an operator. Also probably the least flexible. Handles only simple use cases such as deployments and upgrades. Moving on to the operator SDK, this provides basically a set of low-level Go libraries that tie into the Kubernetes APIs. Currently, these libraries are only available for Go, but may eventually be ported to other languages as well, possibly Python. It currently only uses or consumes Go code, but in the future will evolve to consume Ansible playbooks in the same method that the Helm app operator consumes Helm charts. This is a highly flexible means of developing an operator. It does require some knowledge of Go, but it does expose some low-level CRUD operations, create, read, update, delete, that can be consumed by the SDK, in addition to listing and querying options to be able to query resources in the Kubernetes API. The raw operator, these are written in Go without the provided SDK, and increases your code complexity quite a bit and requires extensive knowledge of Kubernetes internal APIs. So for code clarity, I mean, there's really almost no reason not to use the SDK at this point. But you can get that on github.com/operator-framework. Here we go over the operator maturity model. This just kind of visually shows the range and complexity in operators from just basic, simple, automated rollout and installation to highly complicated autopilot, system admin level automation. You'll see Helm here, as spoken on the previous slide, covers installation and upgrades. Ansible playbooks cover roughly the same space, possibly a little more advanced into lifecycle management as well. But Go-based operators cover the whole spectrum there. Here we go into terminology review. You'll see a lot of these acronyms and things referred to in the operator space, and as we move on. So just to kind of give you a brief introduction to these and kind of define what these are. First, we have custom resources, and we've spoken about this. These are Kubernetes resources of a custom kind, besides what already exists in Kubernetes, such as pods, services, deployments, replica sets, daemon sets, etc. The custom kind is what we define, and is pretty much usually the name of the application that we're managing with the operator. These are described in YAML or JSON syntax, just like other Kubernetes resources, as we've seen on the previous slide. And also, as mentioned, this is the means of user interaction with the operator. So, this is kind of that instruction set where we tell the operator, hey, this is the size of the deployment, we want to deploy of this particular type of app. Custom resource definitions. This is a JSON or YAML syntax file, and it's used to register a particular custom resource with a cluster. So it basically describes to the Kubernetes cluster, tells it, hey, we're creating a valid resource named this with a kind, say, example app, and just kind of defines the the nouns or whatever used to reference that with the client tooling. Say in the case of example app, you could type OC get example app or example app. So it defines like singular and plural values, but that's probably going a little too in depth for this point of the presentation. So we'll go more into that in a future installment. Cluster service version. This is also a JSON or YAML syntax file for metadata. This is basically used by the operator lifecycle management, which as of OCP 3.11 is baked into OpenShift. It contains the product name, description, the operator image location, which registry the operator image is located at, where it's being consumed from, and also like an embedded icon. It also encapsulates the operator deployment, RBAC.YAML, and CRD as well. So it's just a single kind of a templated file that contains everything we need to launch an operator in Kubernetes. And it, like I said, it's built into or part of Operator Lifecycle Manager. That's the unit that the Operator Lifecycle Management consumes, and it essentially acts as a catalog listing. The Operator Lifecycle Manager itself, or OLM, is part of the operator framework, already stated, being included in OCP 3.11, OpenShift Container Platform. A Helm chart, or set of manifests describing Kubernetes resources. These are used for package management. So this is a way just to can all these various Kubernetes manifests, all these resource types, everything needed to package or bundle an app or operator in this case, and deploy that onto Kubernetes. Here we go over kind of just a way to grossly simplify Kubernetes and containers and how they interrelate. We'll use the Lego analogy. Containers in Kubernetes are similar to Lego blocks. Containers are basically the building block itself. That's what we're building, kind of a higher level construct out of. Kubernetes is the platform or the build surface. It's the table we're working on. It's the platform for running containers, for orchestrating and managing the containers. But obviously, if we want to build something cool out of building blocks or Legos, we're missing a few key things there, such as this Millennium Falcon, for instance. Operators build cool stuff out of Lego blocks or containers. They give us those last two things. Instructions in the form of custom resources. This is where we tell the operator, what we want to build, what we're telling the operator, exactly what we want it to do. But it also has the logic it needed to read the instructions and build what we want to build out of Legos. So the Lego builder is similar to a kind of a human-esque Lego builder. But I'd like to thank you all for attending today. It's been great hosting you. Hope you join us again for our next installment, which is setting up a Kubernetes environment to deploy operators into. But anyways, thank you again.